afternoon, everybody. Welcome, everyone, to EPA's Cumulative Risk Assessment 2013 webinar series. The webinar series is co-sponsored by EPA's Risk Assessment Forum, Cumulative Risk Assessment Technical Panel, and EPA's National Center for Environmental Research. And we are very happy that you all can join us today. And we are just thrilled that we continue to get high response for our series. My name is Devin Payne-Sturgis, and I'm with EPA's National Center for Environmental Research. I am the Assistant Center Director for Human Health. Also with me on the line is my colleague, Lawrence Martin, with EPA's Risk Assessment Forum. We are honored today to have with us a leading practitioner and researcher on cumulative risk assessment and one of EPA's Science to Achieve Results, also known as STAR grantee, Dr. Jonathan Levy. The first part of the webinar will last about 30 minutes, and once Jonathan has presented, we will have approximately 30 minutes for questions and answers and discussion. And I just wanted to mention Jonathan is calling in from Boston, and I just wanted to acknowledge and say that our thoughts and prayers go out to the city of Boston. Since there are many participants on the phone, and in order to ensure a successful webinar, all lines have been muted to minimize background noise. And so I'm going to ask my colleague, Ashley, to go over the ground rules.
While all lines have been centrally muted to reduce background noise, please also use the mute button on your phone if possible to avoid background noise, which can make it difficult for other participants to hear. If your phone does not have a mute button, it can be muted through the computer using the microphone button next to your name on the participants list on WebEx. Please note that muting using the WebEx participants list should only be necessary if you've accidentally clicked on your name in the WebEx participants box. All questions will be submitted using the chat feature in WebEx. These will be compiled and the presenter will address as many as possible following their presentation. To access the participants list and the chat feature in WebEx, please click on the green tab at the top of your screen. This will expand the box, and you can click on the chat or participants, and a box will appear on the right-hand side of your screen. This webinar is currently being recorded and will be made available on the EPA INSER website.
Great, thank you, Ashley. Before we get started, Lawrence and I would like to say a few words about the purpose of these webinars. The purpose of the series is to share and discuss the progress of groundbreaking research on cumulative risk and other related activities to develop and apply methods for assessing the combined health and/or ecological risks of multiple chemical, physical, and/or biological stressors with consideration of population vulnerability. The series will feature scientists from both inside and outside EPA. Assessing or evaluating the true reality of environmental impacts on human health is a major challenge for EPA. Last month, we had a presentation in our webinar on applying cumulative risk approach to drinking water contaminants, where we explored issues of commensurability of effects and common metrics, and how the disability-adjusted life years metric provides a viable solution to this issue. Today's presentation will be on research by one of our STAR grantees to develop and apply novel statistical and analytical methods for community-based risk assessment. In particular, Dr. Levy will address an approach he and his colleagues are using to overcome a major challenge of data availability at the proper geographic resolution for community-based cumulative risk assessment. So now I'd like to ask Lawrence Martin to say a few words about the Risk Assessment Forum's efforts on cumulative risk and how today's webinar helps address important issues for the RAS efforts.
Thanks, Devin. This is Lawrence Martin. I'm the EPA Office of Science Advisor. I staff the Risk Assessment Forum's Cumulative Risk Assessment Technical Panel, which is charged with the development of guidelines for cumulative risk assessment, or CRA. The technical panel has 5 writing teams at work now, working on a draft of the guidelines. It's still going to take a while, but we're making progress. These seminars continue to provide thoughtful insights to CRA methods that the writing teams reflect upon in their work. The RAF CRA Technical Panel first published the framework for CRA in 2003. You can see the link at the bottom of the slide. And this remains the seminal foundation document for our work. One of quite a few, actually, but from the perspective of the technical panel, it is our seminal document. So once again, I'm happy to say that the Risk Assessment Forum is pleased to partner with the National Center for Environmental Research to present these webinars, Cutting Edge Thinking on CRA. Panel members listen to both the speakers and the dialogue following the presentations to gain insights to CRA methods, as well as to hear critiques and conceptual concerns that participants have. Next slide, please. So this is our technical panel membership. We've added a number of new members to the panel to fill some skills gaps that we identified on our writing teams. On behalf of the RAF CRA technical panel, we're really pleased to welcome Dr. Levy to the webinar series. The panel had occasion to work with Dr. Levy back in 2011 on a subcontract to prepare a very nice white paper for a workshop we convened on the integration of chemical and non-chemical stressors. His discussion today is highly relevant to an important CRA question, the availability and quality of exposure data. His approach, I think, is novel, and it appears to provide a method with some degree of rigor that can aid in creating detailed exposure models to address geographic and demographic subpopulations. That's built from publicly available aggregate population data. So I'm really looking forward to the presentation and the following discussion. Back to you, Devin.
Great, thank you. And now I would like to introduce Dr. Jonathan Levy, the 10th speaker in our series. Jonathan's presentation is entitled Simulating Population Characteristics and Exposures to Multiple Stressors for a Community-Based Cumulative Risk Assessment. Jonathan is Professor of Environmental Health in the Department of Environmental Health at the Boston University School of Public Health. He received his SCD from Harvard School of Public Health in Environmental Science and Risk Management, with a BA in Applied Mathematics from Harvard College. And at this point, I want to say something interesting. SCD, I don't know if people are really familiar with that degree, but when I was in school, when we met somebody who had that those initials after the name, we knew they were from either one or two schools of public health, either Hopkins or the other H school, Harvard, that is. Anyway, Jonathan has conducted a number of research projects and is currently working on an EPA STAR grant to develop methods for community-based cumulative risk assessment that includes chemical and non-chemical stressors. His other research interests include air pollution exposure assessment, health risk assessment, with an emphasis on urban environments, multi-stressor exposure scenarios, and issues of heterogeneity and equity. So I now would like to turn it over to Jonathan, and sorry for the little joke.
All right, hopefully everyone can hear me, and thanks Devin and Lawrence for the introduction, and thanks Devin for the kind words about Boston. It seems fairly trivial to talk about exposure modeling to contaminants right now, but here we are nevertheless, and I want to give you a sense of some of the things that we've been working on within our EPA STAR grant thus far. And as Devin mentioned, I'll try to keep my comments to half an hour, so there's plenty of time for discussions. I think there's a lot of things that could be talked through and discussed related to these topics. So our cumulative risk assessment study itself is an effects-based assessment focusing on two health outcomes of interest, ADHD-like behavior or attention deficit hyperactivity disorder-like behavior, and hypertension. And our goal is to look at the cumulative impacts of chemical and non-chemical stressors on those two outcomes. I'm not going to talk actually at all about the health effects side of things other than tangentially. What I'm going to talk about is work we've been doing recently on the exposure assessment side of things, and really two key elements: constructing synthetic microdata and then developing exposure models that link to those data. And I'll explain what I mean by those steps and the rationale for it momentarily. So first, just so that everybody has a sense of what we're talking about, our project is focused in New Bedford, Massachusetts. It's about 60 miles due south of Boston. It's obviously a coastal community on the water, so there's been a lot of fishing activity there historically and currently. There's also been a lot of industry over time, some of which has gone away, some of which is still present. And New Bedford is a smaller city, slightly less than 100,000 individuals. It's probably most known from an environmental standpoint for the New Bedford Harbor, which is a very large Superfund site, designated as such about 30 years ago, related to historic PCB contamination. But that's clearly not the only source of environmental exposures in the community. There's other smaller scale hazardous waste sites in industrial facilities. There's some major roadways that cross through the town. And broadly, it's an older community with an older housing stock, a lot of fish consumption given the demographics and the location. So you could see the potential for considering cumulative risks or exposures across a number of different media and a number of different contaminants. You know, New Bedford's also one of the lower income communities in Massachusetts. I think the per capita income is somewhere in the bottom 5 to 10 of the 351 cities and towns in Massachusetts. About half of kids are in high poverty neighborhoods, and nearly half the population is less than twice the poverty line. And there's elevated rates of a number of key stressors and health outcomes of concern. And here I'll particularly point out the percentage of kids in special education programs in New Bedford. This clearly isn't solely or even, in large part a story about environmental contamination, but it shows that there is a lot of interest in the community in understanding neurocognitive effects and other health outcomes in children. One of the other reasons we focused on New Bedford, other than the cumulative exposure context, is that we had the opportunity to connect with a very large and robust set of data from a cohort study that began in the early mid-90s and has been continuing to the present time. So newborns were enrolled from New Bedford and surrounding communities from 93 to 98. And the goal of this study was to look at neurodevelopmental endpoints, including ADHD-like behavior, our outcome of interest. But it has a host of information available, including very detailed biomarker measures for prenatal PCBs and metals, blood lead for the children over their early years of life, home assessments, and a host of other information. So this provided us with the opportunity to leverage public data resources and the insights from this cohort to provide something that would be very targeted and specific to New Bedford. So broadly, why have we sort of focused on exposure assessment? Obviously, we have a dose response and a toxicity piece of this study, which is central to cumulative risk assessment. But at least I would argue, and we would argue, that in the world of cumulative risk assessment, exposure assessment maybe hasn't gotten enough attention. The issue of understanding joint health effects is very challenging, so that has necessarily required a lot of focus. But I think the exposure challenges have not been appreciated to the extent that they should be. And this includes the need to model exposures simultaneously to a large number of stressors. And because we're interested in vulnerable subpopulations and groups of people who might be highly exposed to multiple contaminants, it's important to figure out not just the broad distribution of these stressors, but correlations among them and individuals or subpopulations who might be highly exposed to 2, 3, 4, 5 different stressors of interest. And because at least these community-based cumulative risk assessments are focused in a small geographic area, to answer this question, exposure models need to be quite resolved both across demographics and across space. You wouldn't want a single exposure model or a single exposure distribution assigned to everyone in a community. You want to capture the nuances associated with location within the community and behavioral aspects. And rarely could you go to a city of 95,000 people, let alone hundreds of thousands or millions of people, and gather exposure data from them. So there's going to be the need to leverage public data resources at some point, even if you do have some population-specific validation data or data from model building. And so this study really is about what we can extrapolate from the New Bedford cohort and how we can tie that to public data. So our fundamental premise was that if you have measurements of exposure, biomarker measures, or other measures on a subset of individuals in a community, you could build regression models to explain that variability and then apply those to the full population. This has been commonly done in a number of different locations. Marilyn Miranda, for example, has done quite a bit of that in North Carolina, looking at lead. It's been done in the land use regression realm, for example, looking at air pollution exposures. So it's a common structure to take a subset of exposure measurements and find a way to explain variability. And so one could do that here if you had a lot of individual level data that included where people live and their basic demographic attributes, things like age, race, and income that we know are important drivers of behaviors that can influence exposures. But the unfortunate thing is that those data don't exist, and this is for privacy reasons, among other things. If you knew exactly where someone lived at, say, the census tract level and you knew their basic demographics, you could identify them as an individual pretty readily. So these multivariate attribute data, these individual characteristics, which are referred to as microdata, don't have much geographic resolution. That information is masked if you look in the census, for example. And if you get data down to the census tract level or other very fine geographic resolution, you can only get one or maybe two variables at a time, occasionally three, that are cross-tabulated, but you can't get this suite of information. And again, both of these are to try to retain privacy of the individuals filling out the census. So if you look at this map, which shows New Bedford, it's a little bit hard to detect it here, but the blue number 04500, which is sort of in the middle of the screen here, this is what's called a public use microdata area, which is sort of jargon for a fairly large geographic domain where you can get microdata. And this includes New Bedford, which is in the center, but also a lot of surrounding communities. So you can get detailed individual level data only at this very broad geographic extent, or for these census tracts, these very small spaces in gray in between, you can get only a small number of variables. So we were stuck a bit on trying to figure out how to get the best of both worlds, the geography and the demographics. And it turned out that people had really figured this out quite some time ago outside of the world of environmental health, and specifically micro-marketers, people who want to do targeted marketing for products, had built simulation techniques to create essentially a synthetic census where you knew both the geography and the demographics. And so this has been done for decades in that realm, and demography as well. And only very recently has it been linked to anything in the realm of public health. I saw one publication in 2012 using it. But it really provides a lot of key information that you might want to be able to do cumulative risk assessment. Again, knowing where people live and a lot of their basic characteristics that could influence exposure. So in this study, we decided to try to develop synthetic microdata for New Bedford in a way that could inform our exposure models. So given the amount of time, I didn't want to spend much time on the details of the approach, but the general strategy is fairly intuitive. You have microdata, which might represent, say, 1% or 5% of the population, and you want to basically select those individuals from the microdata who could match up to census information for individual variables for, say, a census tract or other locations. So you grab a random subset of people, you put them into one of these geographic areas, say a census tract, and then you look at the constraints that you have set, the basic information from the census. If you matched it, that's great. You probably won't match it with a random subset, and so you sequentially swap out people from the set that are in versus the set that are out to get closer and closer to your constraints until ideally you have a perfect or near perfect fit. So this is the probabilistic reweighting using simulated annealing. It's just the statistical means to follow this sort of intuitive 1, 2, 3 process here. For those who are on the statistical side of things, it's like a standard hill climbing algorithm, but just with a little bit more complexity to it, so you don't end up in a place that's just a local maximum and not a global maximum. So you can follow this approach, and the question is, how do you know if it works? And so we focused on 3 ways to try to figure out if it worked. One is just internal to the process. You want to obviously make sure that you match the constraints that you set out, because that was the point of the whole thing. The second, though, is to see, do you reasonably represent other microdata fields that were not part of your constraints? So other information in the census, can you replicate what is observed for that variable in the census? So that would show that your synthetic population is pretty robust. And then, because what we really care about is building exposure models, you want to be able to link that in with a model of exposure to key stressors to get at the spatial and demographic distribution. So I'll talk through these 3 levels very briefly. The data we used are from the American Community Survey. This is from the U.S. Census, and we took the most recent 5-year American Community Survey, where you can get a 5% sample of the population. So this was about 9,000 and change people from New Bedford and surrounding communities. And then we applied a number of constraints that were available at the census tract level, and individual variables that you could get for census tracts in New Bedford. some for individuals, some for households. And you could see a lot of these are individual variables, and there's a few times that there's some modest cross-tabulation, sex by age, for example. So we applied these 13 different constraints, 8 individual and 5 household, to the microdata, ran it through the simulation, and then here's what we got. So this is the first level of validation, which is, did we match the constraints reasonably? And a general rule of thumb for goodness of fit here is that you want your total error per household to be less than 1. And so that's the y-axis on this plot, and that's the blue line. And you can see pretty quickly that we fell well below the blue line in all cases. And in fact, most of the constraints were met with perfection. There was a small number where we didn't meet them with perfection. That's in part because if you look at a 3-way cross-tabulation, for example, sex by age by educational attainment, the numbers start to get very small and it's hard to perfectly replicate. But we did a good job of matching the constraints, which is good. And then we decided to try applying it to another microdata field not in the constraint set to see if we could capture it. So this is just one of the series that we looked at, looking at the percentage of multifamily homes, which is potentially important to understand residential exposures or in-home exposure. The left side here is what is reported from the census, and the right side is what exists in our synthetic microdata. And you can see it's not a perfect representation, but the broad spatial patterns are pretty well captured. The correlations between census tracts were above 0.9, I think 0.93 if memory serves. And so you can see it does a reasonable job of depicting the general patterns. Now the toughest part then is to connect this in with a relevant exposure model to give us some interesting insight. And so our first proof of concept was looking at cigarette smoking, where there's a lot of good data available. So we got data from the Massachusetts Department of Public Health, from BRFSS, a large CDC survey, and where a number of individuals in that survey were identified as being in New Bedford. So we took those 4,000 some odd people from New Bedford, and we built a model to predict the likelihood of smoking as a function of all those demographic variables we just created from the census, from the synthetic microdata. And you can see there it's a pretty broad list of demographic variables. We coded it so there was a one-to-one match. So the fields and how they were constructed are identical in the BRFSS as they were in our synthetic microdata. So we could then take this model and directly apply it. So smoking regression model showed patterns that have been shown elsewhere. There's nothing too surprising here. You know, there's some modest differences in patterns because this is specific to New Bedford, not a US-wide model. But you know, there's a lot of age and gender-related and education and income-related patterns in smoking. And the punchline then comes out in this figure, where we can determine the percentage of smokers by census tract in New Bedford. And so you can see here spatial patterns where you have higher rates of smoking in some of the more central downtown areas and lower rates elsewhere. To be clear, this is not something that could necessarily be directly validated. The point of doing this is to generate data at a spatial resolution that you could not obtain through available surveillance data. So you could not directly validate this map per se, but we could look at the demographic patterns and see how well it replicates other data. And so this is an internal validation. We're comparing what the BRFSS reported for the total population and for individual demographic groups with our estimates, which are the red dots. And you can see in each case, the red dot falls within the 95% confidence interval of what the BRFSS reported. So we were able to replicate the overall smoking rate in New Bedford, which is actually quite high, on the order of, say, 27, 28%, as well as the gender-related patterns, the race-ethnicity patterns, educational patterns, and so on, some of which are a little bit different than what you see nationally. So by being able to build a local model and link that to these local synthetic microdata, we were able to capture nuances of smoking in New Bedford that you normally could not capture. So with that, we could then build to other stressors. So I'm going to briefly run through a few examples and then broaden out to the big picture. So focusing today on a few of the key stressors that were related to ADHD-like behavior. And so while I'm not going to talk about the outcome metric here today, just so everyone's on the same page, I think people are familiar with ADHD and its general definitions and structures, what we focused on in our analysis is ADHD-like behavior. So behavioral scale that can be looked at as a continuous metric using psychometric tests and other behavioral rating scales. And what we did first, procedurally, was conduct a very broad-based literature review to look at candidate factors. And to be clear, this is not to say that everything on this list we think is causally associated with ADHD or ADHD-like behavior. This is just everything that was ever mentioned in a publication, or at least a publication that we were able to find that was tied to this outcome. So this was the universe of things under consideration. And then we did some triaging to say, what's potentially causally associated and what do we think might be spurious or have, weak evidence in the literature. And then from a practical standpoint, for which factors could we build exposure models for New Bedford that can leverage this synthetic microdata and give us the appropriate geographic and demographic patterns. So our conceptual model included a subset of those chemical stressors, DDE, mercury, PCBs, and lead, all of which were collected in New Bedford cohort, as well as metrics that might be related to psychosocial stress, which has also been associated with ADHD-like behavior in the literature. And so going to focus just momentarily on PCBs, which has been certainly of primary attention for the cohort, New Bedford cohort itself, and for the community at large, given the Superfund site. So we can build a regression model explaining variation in PCBs, and this has been done in studies published in the literature in the past based on a variety of characteristics, demographics like mom's country of birth and age, exposure routes related to, for example, eating fish skin or dark meat, organ meat, broad secular trends, and other demographics. So this regression model confirmed what had been built elsewhere. The problem, though, is that you cannot ascertain all of this information in a multivariate way from available public data. So we could use the New Bedford cohort to understand these risk factors, but you can't generalize this to the general public. So you could then build a model that throws out everything that is not available from the census or from public data, and you're left with mom's country of birth, age, and income. And you can see the R-squared there only goes down a small amount from 0.36 to 0.34. The problem is one of the main reasons, or probably the main reason we're doing this, is to try to inform public health interventions and to be able to inform the community about measures that could be taken to reduce your exposure, and going to the community and saying, essentially, your exposure is a fait accompli. If you tell me your age, country of birth, and income, I'll tell you your exposure, and these are things that you cannot do a whole lot to modify. It's not terribly satisfying. So as our next variant, we said, let's take some of these key exposure routes, like organ meat or fish consumption, or things like breastfeeding and smoking that can also influence PCB levels, and let's predict those based on these demographic variables. So it's still tied to the demographics of the population, but there's an explanation of the rationale for those fields, and in particular, if something like mom's country of birth is significant, is it significant for something related to historic exposure, or because it has something to do with breastfeeding, organ meat consumption, fish skin or dark meat consumption, and so forth. So we then built a model that had this multi-level structure. You could see the R-squared improved modestly, but more importantly, we were able to determine some of these key behavioral predictors, not just strictly demographics, and then determine significant predictors of those. So then if we have information on country of birth, age, education, marital status, income, all these other variables, we can then determine these risk factors and try to estimate exposures. So we did that, and we applied it to the synthetic microdata and came up with a map like this. Now, one thing to say here, which I probably should have stated earlier, I'm presenting this in maps as a good way to summarize the information and give people a sense of perhaps spatial heterogeneity in at-risk populations. The dangerous thing in presenting these things in map form is that this exposure model is really about food consumption patterns, demographics, and so on. There's nothing in the model related to geography per se. It's related to the composition of people in those geographic areas. So people's eyes are drawn toward perhaps the darker shadings versus the lighter shadings, and perhaps some thoughts about what the key sources could be, but it's really about the demographics of the populations in those locations and the degree to which that can help us to explain the variability in PCB exposures. But that caveat aside, that very strong caveat aside, you can then take these maps and overlay them, or in this case put them side by side, and start to get a flavor of where are the people who might be, for example, at higher risk of having elevated PCB concentrations and elevated rates of smoking. And then you can look at other risk factors. So just as one example of a non-chemical stressor that we thought was indicative of psychosocial stress, we looked at this home observation for measurement of the environment, or home score, which has been shown epidemiologically to be associated with ADHD-like behavior and is somewhat of a proxy for parental stress. It's mostly about the quality and degree of interactions between the mom and the child, but it certainly is indicative of broad-based parental stress. And so we looked at a couple of different subtests here related to emotional and verbal responsivity and organization of the environment, and took the subset from the New Bedford cohort that were available. And for this emotional and verbal responsivity scale, which we hypothesized was a little bit closer to stress, we built, again, a demographic predictive model based on the usual suspects, and then could create another map analogous to the previous ones, where here the darker shadings indicate more no responses on the home score, which is basically a higher risk setting, a higher stress setting. So darker shading, again, here indicates a worse situation, with, again, the same set of caveats that this is really about how populations are distributed rather than other factors by themselves. And again, you can then overlay these and start to look at communities that might be at elevated risk across multiple factors. And this comparison obviously is most visually appealing looking at it graphically and geographically, but because we have exposure estimates for each of the simulated 95,000 people in New Bedford, we can look at it across all sorts of demographic subpopulations, geography by demographics, as many different dimensions as one might like. And just as one final risk factor, and then I'll wrap up, we looked at crime density data to get a sense of community violence, which can be its own pathway toward stress in the household. And this is density of crimes per square kilometer as reported by the New Bedford Police Department and then geocoded. And so you can now have 4 maps and start to see where, again, the places that are low risk for everything might be, high risk for everything, high for some, and low for others. So to wrap up and take this to the bigger picture, we thought that this approach worked pretty well to develop the synthetic microdata and tie it to regression models explaining variation in exposure. We were able to develop models for smoking, PCBs, the home score as a proxy for stress, and we also have models not shown for mercury, for lead, for DDE, and so we're able to build this cumulative exposure paradigm with New Bedford specific data. And the key here, I think, is that while we used cohort data for New Bedford, the framework and the approach are entirely generalizable to other settings. It's really dependent on public data sets. The synthetic microdata are entirely derived from the census. You can do that for any community that you choose. And it's just a matter of having sufficient validation data or other exposure data available for the community with the associated demographics and geography so you can map the two things together. And I think by not relying solely on demographic predictors, by having this multi-level structure, we are able to focus on really exposure pathways and risk reduction strategies and not have a model that feels deterministic. So what we're doing now within our STAR grant is obviously building the rest of our exposure models and doing it in a way that's linked to structural equation models that tie those exposures to the 2 outcomes of interest, ADHD-like behavior, which is being built up with data from the New Bedford cohort, and hypertension, which is being built up from data from NHANES. We've also implemented a survey in the community. As a side point, you'll note the New Bedford cohort was largely recruited in the mid-90s, and so there's questions of whether the demographic predictors developed in the 90s are meaningful for New Bedford today. And so our community survey is trying to help us understand how the community has changed over time, and especially how the predictors of things like organ meat consumption or smoking that show up in these models have evolved over time. And then pulling this together to help better highlight risk reduction strategies that can be implemented by individual residents of New Bedford as well as at broader policy levels. So just to wrap up, I want to acknowledge my collaborators, Patricia Fabian and Jeanette Peters from BU, Susan Korek, who is the PI of the New Bedford cohort from Brigham and Women's Hospital, and then Maria Rosario, Bob French, Arlene Ayala, Jordan Pina, and Maria Mojica, all from North Star Learning Centers, who is our community partner in New Bedford, and again acknowledging the STAR grant for which this research could not have been done with our usual caveats. And I'm happy to answer any questions about our work.
Great. Thank you so much, Jonathan. We're really grateful you were able to join us today and present this exciting information from your research grant, your STAR grant, as part of our series.